video to help you through the activity on defining acids and bases and on neutralization reactions. Let's start with two common definitions for acidity and basicity. According to the Arrhenius definition, which is one of the oldest definitions of acid and base behavior, an acid is something that produces hydrogen ions or protons by dissociation when it meets water. In this example reaction, hydrogen chloride is dissociating into a hydrogen ion and a chloride ion. Here's another example of the same reaction in water. It's written differently because water is a reactant, and instead of a hydrogen ion or proton, the product of this is a hydronium ion. The definition of an acid still fits in this equation. HCl is dissociating and making H3O+ in water. H3O+ and H+ are the same thing in a water solution. These two reactions are essentially identical, or they're two different ways to represent the same thing. In water, hydronium ions are essentially the same as hydrogen ions because whenever hydrogen ions are in water, they glom on to the lone pair of electrons on a water molecule and produce H3O+. The equation for this reaction is written at the top of your activity. The Arrhenius definition for a base is that a base is anything that produces hydroxide ion when dissociated in water. A hydroxide ion is a complex ion that we've talked about before. Here's an example. Sodium hydroxide is an ionic compound that dissociates into sodium ions and hydroxide ions. Therefore, sodium hydroxide is a base according to the Arrhenius definition because it produces hydroxide ions in water. Let's talk about the Bronsted-Lowry definition. A Bronsted-Lowry definition of an acid or a base is almost the same as an Arrhenius definition, except that it doesn't specify that the reaction must take place in water. Notice that the Arrhenius definition defines an acid or a base as its reaction when dissociating in water. In the Bronsted-Lowry definition, an acid or a base is defined based on where a proton moves to and from. An acid is defined by something that loses a proton during the reaction. Here are the same two reactions that I wrote above here. Let's look at this in light of the Bronsted-Lowry acid definition. HCl loses a proton and becomes Cl-. Therefore, HCl is an acid by both the Arrhenius and the Bronsted-Lowry definitions. Let's look at the second reaction. Once again, HCl loses a proton to become Cl-. It's still an acid. In the Bronsted-Lowry definition, a base is something that accepts or gains a proton during a reaction. Let's look at this reaction again. Notice what's happening to the water. Water is going from H2O to H3O+. It's gaining a proton and therefore it fits into the Bronsted-Lowry definition of a base. The Bronsted-Lowry definition for acids and bases also spurs the concept of conjugate acid-base pairs. A conjugate pair is any two things that differ by only a proton. For example, in the second reaction here, hydrogen chloride and chloride ion are different only by one proton. Therefore, they are a conjugate pair. Water and hydronium ion, or H3O+, also differ only by a proton. Therefore, these two things are conjugate pairs. There are 6 strong acids that I'd like you to know, and 4 strong bases. I'd like you to notice the trends in these things so that you don't have to memorize this from scratch. Notice that the acids on the left-hand side of this box are all acids that are made from hydrogen bonding to complex ions. These are all complex ions that you've seen before. Sulfate, perchlorate, and nitrate, when combined with hydrogen, make strong acids. The other 3 in this box are acids of halogens. They're hydrogen combined with the group 7 elements, except for fluorine. If you look at your periodic table, these are the elements right here, chlorine, bromine, and iodine. When combined with hydrogen, make strong acids. Hydrogen iodide is the strongest in the series, and hydrogen fluoride is too weak to be considered a strong acid. There's one more thing I would like you to know. Hydronium, or H3O+, as well as hydrogen ion, or protons, are also very strong acids. All of the strong acids produce this very strong acid when they're exposed to water. Now I'd like you to look at the strong bases that are shown here and notice what's similar about them. All of these strong bases have hydroxide as part of the molecular formula, OH-, and the counterion, or the positive ion, is a metal from the group 1 or 2 of the periodic table. Anytime you see hydroxide with a metal from group 1 or 2, you can assume that these are strong bases. Now I'd like you to practice. Pause the video and try the questions that are on the second page. In question 1, I'm asking you to identify the reactants as acids or bases. Let's use the Bronsted-Lowry definition. The Bronsted-Lowry definition will be the most useful one for you to remember. The Bronsted-Lowry definition of an acid or a base is dependent on the gain or loss of a hydrogen. Anything that loses a hydrogen is an acid, and anything that gains a hydrogen is a base. In this first reaction, carbonate ion gains a proton, and therefore it is a base. The water loses a proton, and therefore water is an acid. In the second reaction, hydrogen sulfate loses a proton, and therefore it is an acid. You might also recognize this as one of the 6 strong acids I asked you to know. Water, on the other hand, gains a proton, and therefore water in this reaction is a base. Notice that water can act as both an acid or a base depending on what it's reacting with. Notice that acid and base here are used to describe chemical reactivity, and not necessarily what you think of when you normally think of an acid or a base. The terms acid and base now are going to be used to refer to the transfer of hydrogen ions. Strong acids and strong bases are the ones that you want to avoid and are the reasons you wear your lab goggles and gloves in lab. Okay, now number 2, you just want to circle the compounds that are listed in the strong acids. Nitric acid, sulfuric acid, and hydrochloric acid are strong acids. Hydrogen cyanide is not a strong acid. This is a carboxylic acid, so it's a weak acid, and HF is also a weak acid. In number 5, I'd like to point out that things that completely dissociate in water are ionic compounds. But now you need to add to that list strong acids and strong bases. If you don't know why, look at the very first page of your activity. Notice that it tells you that strong acids and strong bases are things that completely dissociate in water. These things are also strong electrolytes. Things that dissociate completely in water are ionic compounds. Both D and F here are ionic compounds. Strong acids also dissociate in water. So hydrobromic and nitric acids are going to completely dissociate in water. Strong bases already fall into the first category. Both D and F here are not only ionic, but they are strong bases. Ionic compounds, strong acids, and strong bases are things that completely dissociate in water, and these things are also strong electrolytes. Now let's talk about neutralization reactions. A neutralization reaction is the reaction of an acid and a base to make salt and water. At the end of a complete neutralization reaction, there should be no more acid or base present because it is completely neutralized into water and salt. In the next part of this activity, we're going to learn how to draw the products of a neutralization reaction if we're given only the reactants. Here are the steps, and these are shown on your activity. The first step is to identify the acid and the base. Let's look at the example that's given in the first problem. Here's HNO3 and KOH. First, identify the acid and the base. These should be pretty easy to recognize if you remember the strong acids and strong bases that are written on the first page of your activity. Nitric acid is a strong acid and potassium hydroxide is a strong base. Now, step 2 tells you to combine all acidic hydrogens and the basic hydroxides in the reactants to form water. The acidic hydrogens are the hydrogens that are on the acid, and the basic hydroxides are the hydroxide ions that are on the base. I'll highlight these in blue boxes. I'm going to take these atoms and combine them on the product side to make water. Now what's left over from the base is a potassium, and what's left over from the acid is a nitrate ion. Now I move to step 3. I'm going to combine the leftover positive ion. In this case, it's potassium from the strong base. Potassium makes a +1 ion, and I'll write that over to the side. The ion that's left over from the acid is an anion, and it's nitrate. It's NO3-, and I'll write this over to the side. To make the salt, I'll combine these two things and write a correct chemical formula. If you don't remember how to do this, please review the information in Chapter 3. The correct chemical formula of this salt will be KNO3. The last step is to check to see if the reaction is balanced, and this one is. Now let's move on to the second example. First, identify the acid and the base. HBr is a strong acid and calcium hydroxide is a strong base. Step 2 is to combine the acidic hydrogens and the basic hydroxides to make water as a product. I will not attempt to balance the equation yet. I'm just going to take these things and make water, and later I'll decide how many of each needs to be combined to make water as a product. Step 3 is to combine the positive ion from the base, so calcium here is a +2 ion, and then the negative anion from the strong acid gives me Br-, and I'll combine these and write their correct chemical formula, CaBr2. The last step is to balance the equation. If you don't remember how to balance equations, review the information in Chapter 5. First, balance the atoms that are not hydrogen and not oxygen. So calcium and bromine. There are 2 bromines on the product side and only 1 on the reactant side. So I'll fix this by placing a 2 in front of HBr. Now the bromines are balanced and the calciums are balanced. The next thing I'll do is balance the oxygens. There are 2 oxygens on the reactant side and only 1 oxygen on the product side. I'll fix this by adding a 2 in front of water. Now the oxygens are balanced. Calcium and bromine are also balanced. And the last thing I'll do is check that the hydrogens are balanced. On the product side, there are 4 hydrogens, and on the reactant side, there are also 4 hydrogens. Now my equation is balanced. Let's try the third example. Sulfuric acid is a strong acid, and sodium hydroxide is a strong base. I'll take the acidic hydrogens and the basic hydroxides, and I'll combine them to make water. Then I take the ions that are left over, and I will combine them to make the salt. In this case, the formula is sodium 2 or Na2SO4. The last thing I need to do is balance this equation. Balance by balancing the non-hydrogen and non-oxygen atoms first. So I'll focus on sulfur and sodium for this example. The sodiums are unbalanced because there are 2 sodiums in the product and only 1 sodium in the reactants. So I'll add a 2 in front of sodium hydroxide. Now my sodiums are balanced, and my sulfurs are also still balanced. Next, I'll balance the oxygens. On the reactant side, I have 6 oxygens, and on the product side, I only have 5 oxygens. I can add 1 more oxygen by placing a 2 in front of water. Now my oxygens are balanced, and my sulfurs and sodiums are still balanced too. The last thing I need to check is the hydrogens. On the product side, there are 4 hydrogens, and on the reactant side, there are 4 hydrogens as well. Now my reaction is balanced. Please try to apply this concept to the next problem and complete this activity. Check the key to make sure you're correct. Thanks for watching this video about acid and base chemistry. If you have any questions, please post them in the comments. And if this video was helpful, please let me know by giving me a vote.